This all-aluminum Mark 8 engine is something else. Okay, remove fuel rail and injectors. I can do that. I gotta wrap this up. I got that strut job to get done today. Come on. There. Okay, let's remove the intake manifold. Loosen and remove 20 bolts and studs, retaining intake manifold to cylinder heads using reverse torque pattern. Wait a minute, reverse torque pattern? I don't have time for that. What difference does it make?
Yeah, you don't have time for that. You got that strut replacement job right after this one. That'll take hours. And you got a softball game tonight. You gotta get moving.
Now, you know that detorque step is in the manual for a reason. You shouldn't be trying to cut corners.
Take that intake manifold off any way you want.
There's a right way to do things and a wrong way to do things.
Come on! It's an intake manifold, not a cylinder head. Who ever heard of detorquing an intake manifold?
Perhaps it's because this engine has an aluminum block.
Aluminum schmuminum.
Isn't this the same fellow who told you it would be funny to put a tack on your 8th grade teacher's chair?
Hey! That wasn't my fault. Who knew she would sit down without even looking? Hey, it was just supposed to be a joke, okay?
All right. I'm not going to detorque the intake manifold bolts. Too much time. Let's just get this baby off. Okay, let's pull it. Come on. Hey, wait a minute. Now, I removed everything. This thing should be coming right off. This technician has just realized something he learned some time ago, but had forgot. Because he did not properly detorque the intake manifold bolts and nuts, it has become warped. It is irreparably damaged and will have to be replaced. Oops. The purpose of this comprehensive training program video is to make Ford and Lincoln Mercury dealership technicians aware of the fact that aluminum engines must be serviced differently than cast iron block engines. Aluminum engines are unique and must be treated as such. As of the 1993 model year, Ford Motor Company offers 2 all-aluminum engines. The new Lincoln Mark 8, which is equipped with a 4.6-liter dual overhead cam 32-valve V8, and the new Ford Probe GT, which features a 2.5-liter dual overhead cam 24-valve V6 engine. While this video will feature these 2 vehicles, the information and service procedures contained here are meant to be general in nature and not necessarily specific to any particular aluminum engine. As we approach the year 2000, you will be seeing more and more aluminum engines from Ford Motor Company, as older cast iron block designs are replaced with new, lighter, and more efficient aluminum power plants. This video is divided into 2 sections. The first discusses aluminum's general characteristics as a metal, and contrasting aluminum with cast iron or steel, we'll take a look at how those characteristics affect engine design. The second section of the video will be devoted to special concerns Ford and Lincoln Mercury dealership technicians need to be aware of when servicing aluminum engines. Aluminum is used in a wide variety of applications, from airplane bodies to baseball and softball bats, to bicycle frames and components, to electronic components, to lightweight backpacking tent frame poles, to rowboats and canoes. The primary characteristic that makes aluminum an ideal material for all these applications is the same reason that automobile manufacturers are moving more and more toward all aluminum engines: lightweight. Aluminum is one of the lightest metals on Earth, and by volume has less than half the weight of iron or steel. We can illustrate this point by comparing these 2 Ford Motor Company engines. On the right is the 5-liter cast iron block V8 found in the Mustang. On the left is a 4.6-liter all-aluminum V8 from a 1993 Lincoln Mark 8. The cast iron block 5-liter has a single timing chain, 1 camshaft, 16 valves, and puts out 225 horsepower at 4,200 RPM. Now look at the aluminum 4.6-liter V8. Compare its massive cylinder heads with those of the 5-liter. Notice the 4 timing chains, 4 camshafts, and 32 valves. This engine generates 280 horsepower at 5,500 RPM. Yet these 2 engines weigh about the same amount. By utilizing the latest in automotive technology in conjunction with an aluminum engine block, Ford engineers have been able to design an engine which is more powerful, uses less fuel, produces fewer emissions, and runs smoother without any penalty in weight. Typically, designing a same-size engine with an aluminum block rather than cast iron will reduce the total weight by 30 to 35%. Also, new aluminum casting technology allows engineers to design aluminum engines to be smaller than their cast iron counterparts. Of course, along with being much lighter than iron, aluminum also does not have iron's strength. Certain areas of an all-aluminum engine have to be designed and fastened differently to compensate for this fact. Aluminum is non-magnetic and non-sparking. It is highly resistant to corrosion and conducts electricity well, though not as well as iron or copper. Another characteristic of aluminum is vibration damping. Aluminum is much less dense than iron or steel, and because of this fact, sound and vibration do not propagate through it as readily as they do through steel. Because vibration doesn't propagate well through aluminum, engine knock is harder to detect. And for this reason, the Mark 8 4.6-liter engine is equipped with dual knock sensors instead of the single sensor used on the cast iron version of the engine. Aluminum engine mounts can be made softer, providing smoother idle quality and improved vehicle handling. The surface of aluminum is also much softer than the surface of steel or iron, so you can't use anything which is harder than aluminum to scrape it when cleaning. As mentioned earlier, aluminum is very resistant to corrosion, at least in the way people usually think of it. That is, it doesn't rust. When exposed to the atmosphere or to moisture, aluminum forms a thin, invisible layer of oxidation, which protects it from further corrosion. Another type of corrosion to which aluminum is susceptible and which engine designers and technicians must be aware of is called electrolytic corrosion. This phenomenon occurs when aluminum contacts a dissimilar metal, such as steel, zinc, copper, or lead, and an electric current is flowing between the two metals. When this electric current, which is simply a flow of electrons, passes from aluminum to the other metal, the current pulls some of the electrons from the aluminum atoms with it. These electrons are knocked from the aluminum atom's outer shell. The atoms adjacent to the dissimilar metal lose their non-corrosive properties, and corrosion can quickly set in. Because of this fact, non-aluminum fasteners secured to aluminum engines, including bolts, electrical leads, and ground straps, are often kept to a minimum or plated with a material to keep the aluminum isolated from the dissimilar metal. Another corrosion area which both the vehicle's owner and the technician need to be aware of is corrosion caused by a damaged or improperly filled cooling system. Serious internal engine corrosion can occur if a proper 50-50 mix of ethylene glycol and water in sufficient quantities is not maintained in the cooling system of an aluminum engine vehicle. Look at this component of an aluminum engine ruined by cooling system failure. This type of corrosion is called cavitation. The surface of the coolant passage has literally been eaten away by internal engine corrosion. Again, it is imperative that the cooling system be kept full with a 50-50 mixture of ethylene glycol and water. Ford Motor Company also recommends the coolant and water be pre-mixed before adding it to the vehicle's cooling system. This will ensure even distribution of the ethylene glycol throughout the system. This discussion of the cooling system leads us to what is the single most significant characteristic of aluminum when addressing its use in automotive engines. This is aluminum's thermal characteristics. First of all, aluminum is very effective in dissipating heat. All automotive radiator cores are now made of aluminum rather than copper for this reason. And heat sinks, like the fins on this air compressor cylinder, are virtually always aluminum. In addition, aluminum reacts very differently to extremes in temperature than does cast iron. It is also more susceptible to damage from overheating. For example, this vehicle's cast iron engine has overheated. Once the engine cools down and the cooling system is repaired or refilled, the engine will most likely be fine. If this vehicle had been equipped with an aluminum engine block, however, and it had badly overheated, the engine would probably have been destroyed. This is because aluminum is more elastic than cast iron. All engines expand slightly as they heat up, but aluminum's rate of expansion is both faster and greater than cast iron's. The same overheating condition, which would not have any lasting effect on a cast iron engine, could very well ruin an aluminum engine. In addition to designing aluminum engines with these expansion characteristics in mind, the cooling systems on aluminum engines are designed differently. On most vehicles, coolant flows into the engine near the bottom, then is pumped through the engine and out past the thermostat at the top of the engine. But Ford aluminum engines use what's called reverse flow cooling. With reverse flow cooling, the thermostat opens to allow the coolant into the engine. In the case of the 1993 Lincoln Mark 8, the incoming coolant is routed through a crossover tube on the front side of the engine to preheat the coolant before it enters the thermostat housing. This design prevents cold coolant from entering a hot engine. Aluminum is much more sensitive to thermal shock, be it hot or cold, than is cast iron. For this reason, strict adherence to specified coolant volume ranges is critical to avoid irreversible thermal damage to aluminum engines. The properties of aluminum do not just affect the design of the engine. Many of these properties, particularly the thermal, significantly affect how the engine must be serviced. Let's take a look at some of these service ramifications. Because aluminum is a softer, weaker, and more flexible metal than cast iron, aluminum engines must be serviced with greater care than is required for typical cast iron engines. Where you might have been able to get away with torque and other specifications which were in the ballpark, that won't do with these new aluminum engines. It is absolutely imperative that fastener torque specifications, cooling system specifications, and proper service procedures be strictly adhered to when servicing an aluminum engine. The old axiom, "close only counts in horseshoes," is very apropos here. Failure to follow established service methods can result in customer comebacks and possible engine damage. Let's look at some of the procedures unique to aluminum engines. As mentioned earlier in this video, aluminum is a soft metal. When removing old gasket or sealing material from a mating surface on an aluminum engine part, never use a steel scraper or putty knife. The steel in the scraper or knife blade is harder than the surface of the aluminum. Using such a tool will scratch or pit the aluminum, as shown on this component, ruined by using a metal scraper. Always use a plastic or wooden scraper to remove gasket or sealing material from aluminum engine mating surfaces. You can also use commercially available spray solvent to clean these surfaces. But be sure to use an evaporative solvent that leaves no residue. Any chemical residue present on a sealing or gasket surface of an aluminum engine will result in a leak. Also, as mentioned earlier, it is extremely important that the cooling systems on aluminum engine vehicles be kept within specification. Probably the most critical service procedures involving aluminum engines are bolt torquing and detorquing. Most technicians are aware of the importance of bolt torquing, but many, like our technician at the beginning of this video, aren't aware of how significant bolt detorquing is on aluminum engines. Being softer, more flexible, and more thermally expansive than cast iron, the various parts of an aluminum engine must be removed and installed with more precision and care. The bolts used to assemble most parts of aluminum engines are called torque-to-yield bolts. This type of bolt is generally used to secure engine components such as cylinder heads, intake manifolds, crankshaft main bearings, and in the case of the 1993 Probe GT, the two halves of the engine block. In general, torque-to-yield bolts are longer and thinner than standard engine bolts. They are also manufactured differently. The threads on standard bolts are machine cut, while torque-to-yield bolt threads are rolled to make them smoother and reduce thread binding. One fact all technicians must be aware of is that torque-to-yield bolts cannot be reused. They must be thrown away. You see, when a torque-to-yield bolt is tightened to specification, it stretches, as do all bolts. But torque-to-yield bolts stretch past the point where they can be reused. Aluminum engine components must be detorqued because of aluminum's inherent flexibility. Bolt tension must be relaxed slowly and evenly around the perimeter of the component. If all the bolts on one side of an aluminum component are loosened, while the other bolts remain tightened, the section of the component where the bolt tension is relieved may deform or warp, as shown in this animated example. This deformation will most likely be permanent. While the deformation may not be visible to the eye, the component will be unalterably damaged. A proper detorque procedure loosens the bolts on a component evenly around its perimeter in 2 stages. The engine repair section of your Ford or Lincoln Mercury service manual shows detorque charts for each aluminum engine component. These charts will instruct you to loosen each bolt in sequence, as shown here. This will ensure that the bolt tension will be relieved evenly and uniformly across the entire component. And remember, when any component is removed, discard the old torque-to-yield bolts. And always install a new gasket before replacing a component. Position the component on the engine and apply a light coating of clean engine oil to the new torque-to-yield bolts. Use a lightly oiled shop rag and wipe the bolt threads, shaft, and the underside of the bolt head. Do not apply a thick coating of oil to the bolt. This will thwart the bolt torquing process. A thin coating of oil on the bolts will ensure good bolt tightening and eliminate thread binding. The vehicle's service manual will also have a bolt torquing sequence chart. You will be instructed to tighten the bolts in 2 stages in the sequence shown in the chart. When all the bolts are tightened to final specifications listed in the service manual, the final step is to tighten each bolt an additional 90 degrees or 1/4 turn. This will stretch the bolt to its full yield. You may notice that the torque specifications on aluminum engines are generally lower than those found on cast iron engines. This is due to aluminum's inherent flexibility and softness. When you encounter low torque specifications, such as those below 15 pound-feet, you should convert them to pound-inches. This torque wrench, for example, doesn't go below 30 pound-feet. Converting pound-feet to pound-inches is simple. Multiply the pound-feet specification by the number 12. For example, 8 pound-feet times 12 equals 96 pound-inches. Using a pound-inch torque wrench will give you more accurate torque readings. And as we've tried to stress here, accurate fastener torquing is extremely critical when servicing aluminum engines. This concludes this Ford Comprehensive Training Program video. We've discussed aluminum's unique physical properties and how those properties affect engine design. We've also addressed how those properties and engine designs affect the Ford and Lincoln Mercury dealership technicians when service is required. These include the importance of proper bolt detorquing and torquing procedures. The importance of this point cannot be overemphasized. We reviewed the function of torque-to-yield bolts and how to correctly clean aluminum engine mating surfaces. We stressed the importance of keeping aluminum engine cooling systems within specification and how to convert pound-feet to pound-inches. As aluminum engines become more and more common in Ford and Lincoln Mercury fleets in the years to come, these service procedures will become the rule rather than the exception. Aluminum is here to stay.